Or you can take an approach so using WA for A general that Drinfeld is developing. And I think he doesn't use delta rings so much, but he uses this universal object. I mean, somehow the Witt vector functor and delta rings are kind of dual ways of looking at the same thing. So it's, sorry? What was the first part of that sentence? Not that I know of, but I think what Bott would say is if you interpret Frobenius lift using delta rings, so you have a morphism such that when you reduce modulo p, of course reduction modulo p now is not flat, which I think is the whole point. So you want to keep all the derived information as well. And then you want the thing you get to be the same as the Frobenius map, which is a canonical map, which somehow exists even at the simplicial level for simplicial, co-simplicial rings. I just kind of made that up, so don't. Yeah, I guess, yeah. I mean, the whole point, one thing I should have said is that remember, phi of x is x to the p plus p times delta of x. You might say that delta of x is a witness to to phi being a lift of Frobenius. So you can choose different witnesses, and the whole point is you want the data of that witness. But that's kind of precisely the thing you do in like higher category theory and simplicial things, where you don't just say that something exists, you specify that as data and add that to your theory. So it's not at all surprising that if you kind of do Frobenius lifts from a kind of the most enlightened derived point of view, that you're also seeing this extra. Derived functor, or do you mean like derivative in the sense of? Yeah, maybe. Like first, yeah, well, it is kind of the first derivative, so yeah, maybe. Let me just press on. Yeah, so this, I've only kind of started to get into this, and there's nothing been published, but this really seems, as far as I'm concerned, this is the way to go. Another point is, here's an exercise. So I wanted to say that, so I kind of reinterpreted, well, we proved that the ring of p differential operators represents the Witt vector functor, and you could think of this, the right-hand side, as kind of being a coordinate independent description of Witt vectors. But I'll say nearly coordinate independent, because of course I define delta as just the ring, the polynomial ring on the higher derivative. So the coordinates are there, but maybe the point is if you give a description of delta, a description of the differential operators in a coordinate independent way, then you would have somehow a coordinate-free description of the Witt vector ring. Kind of a purely conceptual. And then, in fact, that's not so hard. So I just defined delta. Remember, delta is the ring freely generated by all the differential operators. All the iterates of, freely generated by all the iterates of delta, and we call it the ring of differential operators. If you can give somehow a definition of this ring without specifying particular generators, then you would have a coordinate-free definition of the Witt vectors, and you can do that. Another point is that here's a little exercise. The category of delta rings has all limits and colimits. So in the category theoretic sense, so all push-outs, I mean direct limits, inverse limits, push-outs, pullbacks, things like that. And they agree with the ones computed in the category of rings. So that's just, it's a formal consequence of the fact that this, of the kind of the category theoretic setup where you have the two adjoints and things like that. So, yep, which is not completely obvious if you have two rings, A and B, two delta rings. Well, how do you put a delta structure on that? I mean, it's better to take a category theoretic point of view, but of course the answer is delta of A tensor B will be, this is delta of A tensor 1 times 1 tensor B. You know how to compute delta of a product, because that's using the Leibniz rule, and you know what this, of course you want this map to be compatible with the natural inclusions, so then you can work out what that is. But you don't want to say this is your definition, because, I mean, so using some category theory, you can prove this. Question? And the final comment I wanted to make is that you can show that the set of ring homomorphisms from the delta ring freely generated by a ring to another ring is naturally in bijection to the set of ring homomorphisms from A to the Witt vectors of B. So if now I only mention this, so there are no delta rings in this. These are both ring sets of ring homomorphisms. Of course, you prove that by putting the delta ring homomorphisms between delta circle A and W of B in between. But the point of mentioning this is that if we think of A as the function algebra of an affine scheme, then it's saying that I'll use this notation, J of X is the spectrum of the delta ring A freely generates. Then what this equation here tells us is that the B points of J of X are canonically identified with the W of B points of X. So a point of this new variety is, if you like, this is something like a power series ring, or it's like a ZP. It's like, so it's an arithmetic jet. So this is then you say it's reasonable to call J of X an arithmetic jet space. And this Buoyam has pursued this point of view. Oh, well, this is, you might also call it a Greenberg transform, but normally people use the term Greenberg transform when they restrict to B's, which are FP algebras. So you, anyway, Buoyam is really, this point of view is, I guess, due to him to a large extent, and he's really pursued it. And then in Arnab Saha, maybe he's not here, in his lectures, on prisms, things like this will come up a little bit. Okay. Okay. That was just the preliminary remarks. Took a bit longer. Actually, what time did I start? Sorry? 2. Okay. Okay. So now let me get back to the Witt components. So let me just remind you, so delta is this ring of arithmetic differential operators, and we have the iterates of Frobenius, which are in delta. Frobenius itself is just the pth power of the identity map plus p times delta, and then you can iterate that. I did it for phi composed with itself last time, and you get a sequence of operators in here. And then we define theta n in delta join 1 on p. This is the unique sequence of operators starting at n equals 0, satisfying phi composed with itself n times is theta 0 to the p to the n plus p theta 1 p to the n minus 1. And I want to emphasize that this exponentiation here is iteration, whereas these exponents here are just usual exponentiation. So if you like, this corresponds to composition of operators, and this is pointwise exponentiation of operators. So you shouldn't confuse them. Okay, and then the theorem. Sorry? Exactly. So you, right, because once if you've defined everything up to theta n minus 1, p to the n times theta n is then defined, but to solve for theta n, I mean, no, actually you don't, but a priori you do. A priori, sorry, yeah. Yeah, so then the theorem, which is maybe, I don't know, Joyal. This is, of course, a different version of something that's known in some form or another in traditional approaches to the Witt vector functor. Basically, the content of, okay, I should tell you the theorem first before I tell you the content. One is that all the theta n's, in fact, have integral coefficients. So, and then two, they freely generate delta as a Z algebra, as a ring. So in other words, so we might just say i.e., kind of write it symbolically, like this, which of course is so, and somehow the content of this from the point of view of classical Witt vectors is that the classical Witt vector functor defined using Witt components actually satisfies the delta ring universal property. And some version of that, at least if you restrict to the p-torsion free case, which is all that really matters because all representing objects are p-torsion free, so some version of that has appeared in the literature from traditional points of view on Witt vectors before Joyal or Bouillon or anybody else did any of this stuff. So this is that's why I included these names here. Okay, so let me prove this. Right, so the key fact is the one I mentioned last time. Which is that delta, when applied to theta of n, is theta of n plus 1. Oh, sorry, maybe I want to, let's see, assuming that these two are the same up to order n. So assuming that, then this is true plus lower order terms. And that lower order terms, because we're assuming I mean integral lower order terms. Because we're assuming this, there's kind of no ambiguity about what we mean by lower order terms. And then using this, so then you can run an induction if you have this. So then you can, imagine you break theta n itself is delta of theta n minus 1 plus lower order terms and so on. So then you can prove that you can extend this result here to n plus 1. Maybe I'll say it this way. So then delta composed with itself n plus 1 times equals theta n plus 1 plus lower order terms Did he get this thing? Oh, printed the wrong thing. Okay, and then you can prove that up to n plus 1, the two sequences of operators generate the same subring. This is delta of theta of n. But then using that, you can conclude this if you just think about what the, so theta n is delta of theta n minus 1 plus lower order terms. So you kind of substitute this. This will be delta of theta n minus 1 plus lower order terms. And then you can apply the Leibniz rule on delta, and then you'll kind of get delta composed with delta of theta n minus 1 plus lower, so you do. So the key point is to check this, and that's where we actually have to prove something. There's a little argument with congruences, which will be the first time I've actually written out any argument in these series of lectures. So let's do that. Yeah. Or we could you could call it composed if you want. It's is it better to call it composed? It's the same. So delta of theta n is delta composed with theta n. Two operators. So you can think of, in the same way you can think of, no, the composition of operators, not the pointwise product. Composition is, I think, the right word. Yeah. Yeah.
So it's not true that delta n plus 1 is, you wrote.
Yeah. Using this, then you prove this. Yeah. Yeah. Maybe I'll say, then ... Then one proves that by applying this repeatedly, and then you can conclude this. And then that will prove the whole thing by then you let n go to infinity. And of course, this is if you take n equal 0 or whatever, this is you can just check this by hand. So that grounds the induction. Okay, so now let's just prove this. So the point is to expand phi composed with itself n plus 1 times in two ways. So the first one is so phi. When I write something like this, when I take an operator and apply it to something in the ring of operators, I just mean composition. Now we use the definition that right, so to prove this, we're of course going to have to use the definition. So this, we apply phi to that sum, and phi is it's a ring endomorphism. It's not a p derivation or some crazy operator, it's just a normal ring endomorphism. So we can just write this as the sum, I goes from 0 to n, of p to the I, phi of theta I, all to the power p to the n minus I. Actually, what I want to do, this will be, hold that thought, that will be number 2, which will be a little more involved. So let me just do number 1 first, which is, we just do it directly. So then this is the sum, I equals 0 to n plus 1, p to the I, phi of theta I, p to the n plus 1 minus I. So that's just the definition directly in the case of n plus 1. And now, we're continuing with 2. Now we just expand this. So, right, so sorry for the terrible board work. Now I'm going to continue this equality from up here. So, okay, so what is phi of something? Phi of something, it's a Frobenius slip, so it's the pth power of the identity plus p times delta, so that's the same sum, p to the I, theta I to the power p, plus p delta of theta I to the p to the n minus I. I goes from 0. I should look at my notes when I do this. I actually want to separate out, okay. Terribly sorry. So first I want to take one term out of this, the final term. So this is the final term out of this one. So that's p to the n times phi of theta n. And then we have the rest of the summation from 0 to n minus 1. And how I want to write that is pi theta I to the power p plus p delta theta I, all to the power p to the n minus I. And now we use these famous congruences. I think some people call them the Kumar congruences. So if this, what's inside the brackets here, and theta I to the p are congruent modulo p. So then if you raise them to the power p to the n minus I, they'll be congruent to the pth powers will be congruent modulo p to the n minus I plus 1. So this is, I'll write down the answer and then you'll see what I mean. So if you imagine what this is, you'll get a p to the power, the initial term in the expansion will be this, and then all subsequent terms will be divisible by p to the n plus 1 minus I. When you multiply it by that p to the I, you get that all subsequent terms are divisible by p to the n plus 1. Therefore, this equality is true modulo p to the n plus 1. So this is by the Kumar congruences. I don't know if that's is that standard terminology. Kumar congruences, which is that if x and y are congruent mod p, then x to the p is congruent to y to the p mod p squared, and so on. So that's what I'm using right here, and then. Because sorry, I'm not doing a very good job at this. The point is that by induction, that delta of theta I on all the smaller, the biggest I can be here is n minus 1. And so we're in a previous case by induction. So delta of theta I will be some polynomial in the thetas up to I plus 1. But I plus 1 is at most theta n. So whatever polynomial you get when you expand that, it will lie in here. Okay, so then now what do? We just combine these two. So we get that we solve for this term right here. So therefore, p of phi of theta n is, so this goes from 0 to n minus 1, right? This is the same sum as this, except for the final term. So if we say this summation here is congruent to that summation there, because they're both this, then we get that this term here, most of them cancel out, is equal to the final term here. So this is congruent, p to the n, p to the n is congruent to the final term here, which is p to the n, p of theta n modulo p to the n plus 1. And now we can cancel the p to the n's. And we get that those. Where? This exponent you're asking?
Yeah.
Um,
So you are subtracting I from n.
I'm adding n minus I to 1.
Otherwise, this term is not same as that, except the n.
Oh God, did it? Oh, sorry. What a disaster. Yeah, I'm getting things messed up. I wanted to compare it, because I wrote these things in the wrong order. I was comparing it to this. I should be comparing it to this one. And, okay. I'm going to be reduced to just copying from my notes. So what I claim is that therefore p to the n, phi of theta n, is congruent to p to the n, theta n to the p, plus p to the n plus 1, theta n plus 1, mod p to the n plus 1, z adjoining theta 0 up to theta n. So we compare this is equal to that. Therefore, this summation here is congruent modulo p to the n plus 1 to this summation here. All of these terms here match up with the terms in this one, not that one. That was my mistake. They all cancel except for the final two terms here, and therefore this is congruent to the final two terms here in the summation. So this is that, that is congruent to the final two terms, p to the n, 5. Jesus. No, this is, there's no phi here. Sorry, it's all because I wrote the wrong equation first. This is the definition of that. I just stupidly wrote a phi. So the phi is on this one, and then that's perpetuated down through here. And then you get this. Sorry for that. Okay, now we cancel the p to the n's. And we have phi theta n is congruent to theta n to the p plus p theta n plus 1 mod p. And now we expand this. This is theta n to the p plus p times delta of theta n. Then we cancel those two. And now we have another p we can cancel, and we get that, which is what we wanted. Okay, apologies for that. That wasn't. Sorry? No, because we canceled the p. So it's just these two are the same modulo lower order terms.
have cancelled.
Yeah, the P here, and the P here all got canceled. Which is what we wanted to prove. Okay. Okay, so now I'd like to talk about ghost components. So that proves since these Witt differential operators freely generate delta, they provide an alternative system of coordinates for Witt vectors, and which one you want to use, I'll say the usual delta coordinates, or the Boolean-Joyal coordinates, or if you want to use the Witt coordinates, that's up to you in whichever computation you want to do. So some of the Witt coordinates have some advantages, and the Boolean-Joyal coordinates have other advantages. At the end, I'll try to make a little table of the pluses and minuses of each. Yes? This one here. Yeah, you have to apply. You have to do another induction. You have to say. Sorry. Yeah. Theta n is then using the same principle. Theta n is delta of theta n minus 1 plus lower order terms, and yeah. So it's something like a triangular system of generators or something like that. Okay, so the ghost components. So I've told you about the Boolean-Joyal components, the Witt components. Now I'm going to tell you about the ghost components. So we have these elements, the iterates of Frobenius, in delta. And just to remind you, the 0th iterate is, of course, the identity operator. The first one is phi itself. And phi composed with 2 was this one, e to the p plus p delta to the p plus p delta to the p plus p squared delta composed with 2, if I recall. Yeah. So that's what they are. So they don't generate delta even mod p, simply because phi composed with itself n times modulo p, phi is the Frobenius modulo p, so phi composed with itself n times is the nth iterate of the Frobenius modulo p. So therefore in FP, so they simply generate, they all lie in this polynomial ring in one generator, modulo p, which is much smaller than the polynomial ring in infinitely many generators. So they certainly don't generate it, but we can still proceed as if they did, and we can define what would be these coordinates. They just won't be a very good system of coordinates for some purposes. So I'll say nevertheless, we can define a map from the Witt vectors of A, which I want to think of, I kind of always will think of as homomorphisms from the differential operators to A, to an infinite product, as we did before, by just sending a homomorphism alpha. We just evaluate it instead of evaluating it at the iterates of delta, or which would give us the Boolean-Joyal coordinates, or evaluating it at the Witt differential operators, which would give us the Witt coordinates. We'll evaluate them at the Frobenius lifts, the iterates of the Frobenius lift. So this goes to alpha of E, alpha phi composed with 2. So for certain reasons, I like to use angle brackets on the ghost. So this is the ghost map. It's called W. Ghost map. The components on the right are called the ghost components, and I like to use angle brackets for them for certain reasons, which I won't bother to explain. So one thing that's worth emphasizing, I mean, that has to be emphasized, is the whole point, is that the ring structure on the right-hand side is component-wise. It's the product ring structure. And this is because, I mean, the ring structure is always encoded in the Leibniz rules of these operators, but these operators are ring homomorphisms. They're not p derivations or something crazy like that. They're ring homomorphisms, so they're additive. Phi of x is phi of x plus y is phi of x plus phi of y. That means the additive structure is component-wise, and they're multiplicative. Phi of x times y is phi of x times phi of y, so the multiplicative structure is also component-wise. So it's just the component-wise ring structure. So the Leibniz rules for phi composed with n, I'll say, are the easy ones. So the Leibniz rule for addition is the additive Leibniz rule, and the Leibniz rule for multiplication is the multiplicative Leibniz rule. So that's one reason why these ghost components, that's the reason, I guess, why the ghost components are so useful, because you can actually do computations in them because they use the product ring structure. But let me emphasize this. W is not usually an isomorphism because the iterates of phi don't generate delta. So they're not a perfect system of coordinates. Okay, let me tell you what this map does in coordinates. You just unpacked the relations between the phi operators and whatever coordinate system you're using here. So in delta coordinates, or I sometimes say delta coordinates instead of Boolean Joyal coordinates, but I mean the same thing by them. W of a Witt vector, x0, x1, and so on, will be a ghost vector, Z0, Z1, and so on, where Zn is the polynomial expression in the inputs. So I'll just write No, because just think about FP. This will be, we haven't talked about it, but everybody knows. This is ZP, and this is a product of copies of FP. So I'll tip my hand. Well, everybody knows this anyway. If P is invertible in A, then it is an isomorphism. Okay, so what do you? So Z is precisely you just encodes. It's how to describe what the phis are, the iterates of phi are in terms of the deltas. So is the polynomial Z of n satisfying phi composed with itself n times is Z of E comma delta comma delta comma delta n. So for example. W of, I'll do the first component 0 through 2. The first one is just x0. The next one is x0 to the p plus px1. That's just a syntactic re-expression of phi is, of course, e to the p plus p delta, so it's a syntactic re-expression of that. And then the next one is x0 to 0 to the p plus px1 all to the p plus px1 to the p plus p squared x2. And that's just another way of writing that last polynomial there. Okay, so the same thing is true in the Witt coordinates. But now, oops, this is that n? Now, of course, now we want to describe the phi of n's in terms of a polynomial expression in the Witt differential operators. But now phi n is, maybe I'll put a prime to denote for Witt. I'll say, but now with a different polynomial expressions. But now we basically come to one of the few, in my humble opinions, advantages of the Witt coordinates, which is that these are closed form polynomials. In fact, we define the thetas exactly in terms of a polynomial expression. They satisfy relative. I mean, these are the Witt polynomials. These are actually the Witt polynomials. So we can write down the formula that everybody actually knows. And so on. Okay, so that is one of the advantages of the Witt coordinates, which is that the ghost map. So the ghost map is really a coordinate-free map. These are nice. These phi operators are actually, I'm pretty sure this is correct. Shouldn't be hard to show the unique operators which act as ring endomorphisms in the ring of differential operators. And so you can define this map without any preferred choice of generators on your algebra of differential operators. So that's a coordinate-independent thing. The nice thing about the Witt components, the Witt coordinates, is that you can express that map in closed form. If you were going to use the Boolean-Joyal components, of course you can do it, and theoretically it's all just fine, but you might have to do some inductive proof where you just don't write things out in closed form. Okay. Are there any questions on it? Yes? Delta is not equal. Say it again, sorry. I mean, but delta is just a free polynomial algebra. Right, so, yeah. Anything else? Okay. Okay, so anyway, that's the ghost map. These are the ghost components. If you have a Witt vector here, its image here, the components of its image here are called the ghost components. So it's not so well behaved in general, but the phi n do freely generate delta if you invert p. And the reason is just that that delta composed with itself n times is just, I mean, what is delta? It's phi minus e to the p divided by p. You just compose that with itself n times. And as long as you're allowed to have p's in the denominator, so as long as you have, you can expand this out. This will be some polynomial expression in the iterates of phi up to level n. And delta composed with itself n times is that polynomial expression. So I guess this is why they generate it. Maybe a little more thought would convince you that they generate it freely. So this, maybe I should say, so this is 1 on p to the n plus lower order terms. So if you have the phi of n's, the phi circle n's and p's in the denominator, you can recover you can recover the deltas from them.
You're saying that it's not enough to have those.
Yeah, exactly. And this is, I mean, it's completely obvious. Say if you just look at the first two, obviously these two elements here don't generate the polynomial algebra in E and delta. But if you can divide by P, then you can solve for delta, and then they do generate it. So that is basically, that's all I'm saying. Right, so a consequence of this, so if 1 on P, now we're going to consider Witt vectors of rings in which P is invertible. If 1 on P is in A, then what do we have? We have the Witt vectors of A can be identified with ring homomorphisms from delta to A, but A is an algebra in which P is invertible, so we can invert P also on the domain, and we get the same thing. And then this ring here is freely generated by these operators, so then this is equal to the product ring. And the composition is the ghost map. So it's an isomorphism. So therefore, W is an isomorphism. So just to say it again as a slogan, if P is invertible in your ring, then the Witt vector ring breaks up as just an infinite product of rings. So the whole point is when P is not invertible, and also when P is even 0 or nilpotent, say, the structure is non-trivial. The question? Sorry? What becomes a power series ring? Which Witt vector? Sorry? Yeah. Power series ring over what? A. No, W of A is not a power series ring over A. If it's a non-zero, I mean, A usually doesn't map to W of A. You basically need a delta structure to get a map from A to W of A. So W of A is an enrichment of A, it projects to A, but it doesn't map back. Yeah, not as a ring homomorphism. Even as a monoid, you have the Teichmüller map, but
Looks like ours reading was not.
Yeah. I mean, of course, you know it for W of FP, but okay. So here are a few exercises. So if A is p torsion free, then W is injective. And I think this is really important because it tells you that you can you can view, so i.e. the Witt vector, the ring of Witt vectors can be identified with a subring of a product ring. Of course, how it sits in there is very non-trivial, but still, if you want to do a computation, you can always do it in the product ring, if A is p torsion free. Okay, so for example, you can work this one out that in the case where A is Z, you can actually say what it is. So it's the set of vectors, A0, A1, and so on, integer vectors in the product ring such that AN plus 1 is congruent to AN mod P n plus 1 for all n. So you could think of it as, it's a p-adic Cauchy sequence, actually, of integers. It converges at a very specific rate, but it is a p-adic Cauchy sequence. So you can actually take its limit, right? So exercise 3 is, W of z goes to zp. This is the limit of an, the p-adic limit of an, as n goes to infinity. Not a category theoretic limit, an actual p-adic limit. that you have a completely well-defined map, and so then the exercise is to prove that that factors through W of FP, and the resulting map's an isomorphism. So from the point of view of ghost components, the map from W of Z of W to FP is take the p-adic limit. These are ghost components, right? This is the ghost ring. These are the ghost components. One thing I like about this is that you can imagine drawing the spectrum. So you have a bunch of, say you truncate at a finite level, you have a bunch of copies of spec Z, but they're all glued together modulo P to higher and higher orders. So for instance, for length 2, so the first component is glued modulo P, in other words, transversely to the 0th component, and the second component is glued tangentially to glued modulo P squared to the first component, so tangentially. So it kind of looks like that. Each of these is a spec Z. We have a bunch of copies of spec Z glued together modulo higher and higher powers of P to different components. And that's kind of a good that will always happen, although the gluing will be much more complicated in general. So how do we, one thing I think I should say, maybe it's not strictly necessary, but I think it's maybe important, how to do a computation in W of A. So the point is here, A is general, so it might not be p-torsion free. So first thing is you make it p-torsion free. So choose a ring mapping onto it, which is p-torsion free. 2, you lift the computation to W of A tilde. So do it in whichever way you find, so choose whichever A tilde you find most convenient and lift it in whichever way you also find most convenient. 3, compute in the ghost ring so this Witt vector ring is a subring of that. You can do whichever computation you want in the ghost ring. This is easy. This is the whole point of the procedure. And if you like, the key step is the easiest one. You just do the computation in the product ring. And for your result necessarily lies in the Witt vector ring. If you're doing a ring, because it's a closed subring. I mean, it's a subring closed under addition and multiplication. Lies in W of A tilde. And now, if you like, you can rewrite the answer in your favorite coordinate. On W of A tilde, and then finally map back down to W of A, and by general nonsense, the result is independent of all the choices you made. So here's a little example. There are going to be some better ones, but this is what I thought of this morning. So if x0, y0, x1, y1, and so on are square 0 elements in an FP algebra, compute the sum well, in whichever coordinates you like, the Witt coordinates or the delta coordinates or so on. Yeah, I'm a little disappointed in this exercise because I think it's actually too easy. There'll be I think there's some better exercises which just didn't come to mind this morning, which would really illustrate the utility of this point of view. I just wasn't able to think of any in the time I had. Okay, so let me finally say what Teichmuller lifts are from this point of view. It's very easy. Well, and I want to do it in a coordinate independent way, but the coordinates are also very easy. So say A is a ring, and we can form W of A, and we can also form the monoid algebra. So we view A just as a multiplicative monoid, and we form the monoid algebra on it, and notice that it has a Frobenius operator, which just sends standard basis element at position A to the standard basis element at position A to the P. That it's the pth power. It's the pth power map on A, so that's a map of monoids. So it induces a map of the monoid algebras. So everything's fine, and it's also a Frobenius lift, right? Because this is. Sorry. This is also A is a multiplicative monoid. Yeah. Otherwise, I would have called it the group algebra. This is a Frobenius lift just because on each of the basis elements that actually is the pth power map. So certainly when you reduce modulo P, it's pth power map everywhere. So therefore, so this is just the canonical, what do they call that map? Augmentation, or it's the one that sends the basis element A to A, which is maybe not the augmentation. Right, that's a nice ring map, and this is a delta. This is also a delta ring. So because it's p torsion free, implies it's a delta structure. And of course, it's just delta, maybe I'll write that down, delta of the generator, brackets A, is 0. Because the Frobenius is literally the Frobenius lift is the pth power map on brackets A. So delta of brackets A is 0. So you get a well-defined delta structure. So then by the universal property, there exists a unique lift. And the image of the standard basis element at position A is then the Teichmuller lift of A. So brackets A goes to, well, brackets A is standard notation for the Teichmuller lift. So the image of that of brackets A under that map, we continue to call brackets A, and we call it the Teichmuller lift. What is it in coordinates? Well, what does an element go to? I mean, remember how you did the universal property? We take all the different iterates of delta applied to that element, and we look at all their images in here, and that's the vector. So brackets A, if we apply delta 0 times, we get brackets A again. We reduce it in this map, and we get A. If we apply delta once to brackets A, we get 0. So its image in here is 0. And then because delta of 0 is 0, if you continue to apply delta, higher powers of delta, you get more zeros. So that's the Teichmuller lift. This is in delta coordinates, but the same is true in Witt coordinates, which everybody knows. The Teichmuller lift of an element is just the element put in the first component. On what? On the monoid, it's not on the monoid, it's on the monoid algebra. Yeah. It's the one where all the standard basis elements are sent to 0 by delta. The argument is since it's p-torsion free, finding a delta structure on this is the same as finding a Frobenius lift. So we do that. We define this map phi by raising all the generators to the pth power. That does define a ring endomorphism. And it does reduce to the Frobenius modulo p, because on each of the generators, it's literally the pth power map. So that, some kind of what? Yeah, it's pretty trivial. Maybe toric. I would like to call it the toric delta structure. I don't know, there's sort of a GM, if you like, lurking in the background here. So for monoid algebras, are delta rings in a particularly transparent way. Not interesting, but important. So I don't want to trivialize it. Yeah, that's right. Any commutative monoid, its monoid algebra will have a delta structure on it, which is kind of why toric varieties are what you get when you look at monoid algebras. So that's okay. So I think I want to finish with a little table. So this is a conclusion. I don't think I've ever given a talk with a conclusion before. So I want to talk about the pluses and minuses of the different coordinate systems. So we have the Bouillon-Joyal, which is the one I introduced with the deltas, then the Witt ones, which were the thetas, and then we have the ghost ones. Okay, so don't take this too seriously, is maybe just my opinion on these things. So from the point of view of the definition, I find the Bouillon-Joyal one's very satisfying, and the ghost is just a product ring. So you can define the ghost ring. You don't need to know anything about Witt vectors. It's just an infinite product ring. So that's very nice. So from the point of view of category theory and universal properties, I think the Bouillon-Joyal ones are good, and the ghost one's sort of good in every respect. But actually, maybe one respect in which it's not good is whether it's somehow a complete coordinate system, which works in all contexts. And there, Bouillon-Joyal and Witt are fine, but not the ghost. So the ghost coordinates, if P is invertible, then they're fine. But if P is not, then they're not fine to greater or lesser degree, depending on how much p torsion there is. Then there's I'm going to run out of space. The phi operator, which kind of everybody else in the world. Well, if you're looking at Witt vectors, people usually call it F. But if you're looking at delta rings, people usually call it phi. So from does it have a nice description? Well, the Bouillon-Joyal one doesn't have a nice closed form description of the phi operator. It has a nice conceptual description, but if you want to write it out in coordinates, there's going to be some messy polynomials. And the same is true of the Witt components. So the ghost components are clear. There, the Frobenius operator is actually just a left shift. The delta operator from the Bouillon-Joyal coordinates, that's also a left shift. The Witt ones are hard. And the ghost ones, I guess in the ghost components, it's pretty easy because you can, all Frobenius is easy, and then addition and multiplication are easy. So, and then I haven't talked about Verschiebung. Verschiebung is the right shift map in the Witt coordinates. So in the Witt coordinates, it's super easy. It's also super easy in ghost coordinates because it's a right shift together with a multiplication by p. In the Bouillon-Joyal coordinates, it doesn't have a nice closed form description. In fact, it just occurred to me that I've never even tried to write out an argument to prove that the V operator exists purely from the point of view of the Bouillon-Joyal components. everything I've always written, I just first prove that the Witt components exist and then describe it in those terms. So, but I think actually there should be a nice argument. But it still won't give you a closed form definition of the operator. So the ghost map, the Bouillon-Joyal coordinates don't have a nice closed form description of the ghost map. The Witt coordinates do, and of course the ghost, here's just the identity operator, so it's, and finally, the Teichmüller is good in all three. In the ghost components, maybe I should say the ghost I mean, everybody knows this, I don't know why I'm saying it. It's just the powers of A, the p power powers of A. Okay, so there are a few topics I didn't talk about. One is, I mean, well, there's sort of infinitely many topics. One is the whole multiple prime theory. You can do Witt vectors with respect to multiple primes, the so-called big Witt vectors if you use all the primes. And pretty much everything I've said works just fine there. It wouldn't be hard to do. There are other variants of Witt vectors like ramified Witt vectors where you work modulo pi instead of modulo p. You could have some inertia, some inert primes, so you could use the q power for Benois instead of the p power for Benois. There are also perfect Witt vectors, which would have been nice to have talked about because they kind of come up in, well, the things that Kieran was talking about. I mean, he didn't use exactly this language, but you could, and then this theta map and so on. Truncations, WN, would have been quite easy to talk about. Truncated Witt vectors where you have only finitely many components. Didn't really have time to do that. And also de Rham-Witt theory. But I guess prisms are, I'd say prismatic cohomology is really kind of the most interesting thing in the world. In particular, it's the most interesting consequence of, I mean, maybe most interesting application of Witt vectors in, like the general theory of Witt vectors in delta rings. And that is what Arnab Saha in the back there is going to give the last two lectures in this series on. So I'll finish here. Okay, yeah, sorry for going over here. The clock, nobody started the clock.